computer. Okay. And I need to share the screen. Okay. Yeah. Okay, welcome back. You see the screen, improving Python, isn't it? You see that. First, I wanted to repeat that these slides are available online. So if you go to our webpage and click on part 1 in the introductory, you get these slides and you can follow through yourself. You can go ahead or you can look behind if you want to. And I will try to walk through those slides and comment on this. So we were discussing last time how to improve Python, and in particular, the ways to improve Python with binding with so-called Fortran, with F2Py, with C++, with PyBint11. And then we also mentioned that there are other options, Weave, which unfortunately is not available in anymore in Python 3, but it's still available in Python 2. There is also Swig, PyCXX, and Ceton. I'm not going to discuss further on it, but if you do your own research, you might just browse through these websites and determine which one is best for you. Each one has some advantages and disadvantages. I believe that PyBint11 is probably one of the best for C, and F2Py is kind of standard for Fortran. But nevertheless, other packages might have their own advantages for certain applications. Now, how do we use those tools to really get the best performance, or basically theoretical performance, on a given computer? We're going to start with Fortran first, with F2Py, and basically the converting Fortran code to Python module is really straightforward. I mean, it's hard to make it more straightforward than it is. So all you need to do is, instead of using Fortran compiler, you just use the compiler, which is called F2Py, and is already built in NumPy environment. So if you downloaded NumPy properly, F2Py already exists. Now, this code here that I'm showing for Fortran is just a normal Fortran code. Okay, so basically anything that you can find on the internet, or anything that you code yourself, if you have a little bit of Fortran knowledge, it will immediately work with F2Py, in the sense that it will create an equivalent Python module. Okay. Now, however, we can make the Fortran code slightly nicer for Python use. Why? Because in Python, the functions are kind of more user-friendly. They have certain features which are better than in typical Fortran code. The example would be, for example, in Fortran, you always need to give the array and also the dimension of the array. In Python, you would never give redundant information, the size of the array, because if you give the array, Python will figure out itself how big the array is, okay? Because as long as you give name of the array, this is supposed to have a particular size, and Python will decode that. In Fortran, you typically need to give this information as well. I mean, in the newest versions of Fortran 90, you don't need to, so there are ways around, but normally in most Fortrans, you do give this information. And you can hide it, for example, through F2Py, this information, so that the compiler figures it out when it transforms from Fortran code into Python module. Similarly, you can have something which is called default arguments in Python, and this is something that Fortran doesn't support. But this transformation with F2Py does support that. So in other words, you can have functions that look as user-friendly as a typical Python module. better than Fortran code itself. Now let me demonstrate this on the case of Mandelbrot cell. So I have here a code which if you downloaded the entire directory, you can go into F2Py and you can see this code in Mandel. So you can see it inside Mandelbrot F2Py, and its name is Mandel F90. Okay, so that's the code that I'm gonna talk about. Okay, you can go there and you can look at it, or you can add comments to the code if you want to, maybe. And so how does this code look like? Well, it's the same as our former Python code, namely it has the inside loop, inside do loop over max steps, isn't it? And then when absolute value of z becomes bigger than 2, we know that this thing is outside Mandelbrot set, and we set into this array, two-dimensional array, the iteration in which we figure out that this is not part of the Mandelbrot set. So we give the iteration number, and we jumped out. If the iteration still needs to be repeated, then we repeat this function f of z. Then there is a double loop outside over this two-dimensional space over x and y. And then I also added here this OpenMP directive. Now, as you can see, OpenMP directive here appears as a comment. So basically, you can completely ignore it. If you don't append in the compilation this minus f OpenMP, this comment is going to be completely ignored. So like it didn't exist. Of course, if you add minus OpenMP, then in the compilation, at the compilation time, then this is going to be OpenMP executable, OpenMP parallelized executable. Okay, so what else do we have here? Now the input to this, we specified here that two-dimensional array of data, nx and ny, is going to be a real array, but with intent out. Intent out, when we use f2py with a variable which is called with intent out, it means that this is going to be returned as a return, like you would return this through return statement in Python. In other words, this is going to be returned as the result of a module of execution of this function. So let me demonstrate this in the manpf.py. So you see, when we call this Mandel is now module. Mandelb is the function name. Here there are arguments to function name, and the result is two-dimensional array data. Okay, so the final result is two-dimensional array data, and because we declared this two-dimensional array as intent out, the result was a two-dimensional array. Okay, if we declare this as intent in out, let's say in out, so in out means that it can be either that has to be input and it can be changed in the function. Okay, in this case, f2py will need data as an input. So for example, in this case, I would need to change, and I would need to give a first argument to be data. Okay, but here the first argument is next one, x, the range, and data is returned. Okay, so the reason the data can be returned, or can be a returned variable in this case, is because we specified here that data is intent out. Okay. Now, however, the other arguments, so x, nx, and y, and max steps, those are all intent in, means that they need to be input variables, isn't it? Input variables. And we specified here that what type, and this 4 means that there need to be four floating point variables. Minimum x, maximum x, minimum y, maximum y, isn't it? And then integer max steps and x and y. Now, in addition to specifying this intent in and out, that helps F2Py to make the code more Pythonic-like, less Fortran-like, but more Pythonic. In addition to this, we can specify things which look like comments. You see, all these things all this line starts with this symbol that stands for comment in Fortran 90. Okay, so this is all commented. Normally, it's being ignored. However, if you use F2Py, then even such comment that starts with a comment and F2Py is not being ignored. Means it's an F2Py directive. Okay, which compiler would normally ignore, but this time it doesn't. So what does it mean? Well, there are several F2Py directives. One possibility is to give a variable default value. For example, max steps here, okay? Fortran doesn't allow default value. Fortran doesn't know what means default value to a variable, okay? But Python knows that. Python supports that. And therefore, we are going to decide that max steps by default is equal to 1,000. So if the user doesn't specify how many max steps there are, then the function will have 1,000 steps. Like the variable max steps was set to 1,000. And so the way you do that is they say F2Py integer optional intent in. Of course, integer is because this variable is integer. If it was floating point, you would specify float, and so on. Of course, these default values can be given only to simple types, which is either integer, floating point, complex, simple types, not arrays. Now, in addition to this, there are other F2Py directives which currently are not active. So you see, I wrote comment and then space and something later. This means that because of the space here, this is actually a real comment. It's completely ignored currently, okay? But I'm just giving an example of what we could write, but currently it's not working, okay? I will explain why. So let's say that you want to deduct or determine variables such as nx and ny from the given array size. So let's say that the data was not output but input. Okay. Unfortunately, in this particular example, I already explained the data is being output from this variable. Okay. Therefore, this code doesn't make sense. But let's say the data here wasn't intent out, but it was like intent in and out. Okay, let's say that this is what we had. Okay, we have. So if it was in out, that means that the user will need to specify data as two-dimensional array. Okay, and it will need to give in Python, it will need to allocate. So therefore, when we get into this routine, we should be able to determine the size of the array because it was specified. In Python before. And then in this particular case, we could use a shape function, which is actually a Python function. So we use shape of data 0. This means that the first dimension of data will become nx. And here similar, we can say ny shape of data of 1. So it means that the second dimension, or basically dimension 1, is going to become ny. And this directive is called intent height. So if we give this so-called F2Py directive, intent height, depend on data, and then specify how it depends on data. We could hide such such variables. Now, again, in this particular case, this is irrelevant, or basically it's not, cannot be done, because our data is intent out, which means it's output. And if it's output, then we need to specify how big the array, we need to have nx and ny as an input variable, because otherwise we don't know the dimension. Okay, so the idea then is that we have just a normal, usual or normal Fortran subroutine. So you can go and read documentation about Fortran and use identical Fortran subroutine as you would write in Fortran, except that you can add here some F2Py directives that make use of such subroutine much more user-friendly if you want to, but it's not essential. You can also skip this step. Okay, now that we have this code, this Fortran code, what do we need to do next? Well, we will compile it and we will use it inside Python. Okay, so how do we compile? Here, if I go inside the F2Py directive, I have something that's called makefile, and that makefile has exactly this information. But let me do step by step. So instead of calling gfortran, we were going to use compiler F2Py, which is kind of, it turns out it's gfortran called with some extra options. Okay, so F2Py -c then has to be name of the source file. In this case, it's mandel F90. I will not add this extra directive openmp for now because it's not essential. Okay, we can just ignore openmp, and then we will add here -m mandel. So what does that mean? I don't know if you all see my screen. Now you probably see it. Huh? So I'm adding this -m mandel. So normally, when you compile something, you give an option -o. -o means name of the output file. But in this case, when you use F2Py, instead of -o, we use -m and the name of the module. So therefore, it's -m because it's name of the module instead of -o as an output. Okay, I'm going to use -m, and then you see that this is basically invoking some Python script that does several things. We're not going to go into details what exactly, but basically it tries to figure out which C++, which C compiler you have, which Fortran compiler you have if you have, and then how to do it. Basically, it specifies that it will find proper compilers, proper source codes, and then it creates a source code somewhere in a temporary directory. Okay, somewhere in a temporary directory, it creates a temporary source code, and then from that source code produces a module. So complicated way, but we don't want to go into details how it's done. The important point is that it didn't give us any errors. So right now it seems no errors. Fortran 77 compiler, Fortran 90 compiler, Fortran 50 compiler. So we try several compilers. Eventually, I guess it figures out that I have Fortran 19 compiler and use this compiling directive. Okay, in your system, it might be slightly different depending on what the system is. Might find some other compiler and use it. But if there was an error, I would get an error message here, which I didn't. So that's good. If you get an error message, we need to debug your installation.
Question.
Yes.
I actually have an error message. It says like limits.edge. No such directly. Like it seems like some packaging C is not.
Something is missing.
Right.
Yes. Yes. Yeah. So that means that there was some issue with installation.
Of GCC?
I would say no. I think that this particular thing probably needs to exist even if GCC was not available. I think that this is part of NumPy. So that's a very unusual thing. It's part of NumPy. And which basically means there is a problem with Anaconda. Maybe you check which F2Pi, because you see my my F2Pi points to Anaconda 3 bin, which means that when I was installing Anaconda, this was immediately installed and things should work, provided Anaconda is properly installed in your system.
So here in my computer, it just don't have the OPT part. Is that a problem?
Don't have what OPT?
Like slash OPT, like you have users wholly.
You don't have slash opt. Well, I don't know, because the question is, why does this system, I have OPT, but I mean, I have certain things in there, but this has nothing to do with Python. So this is a problem that means that your F2Pi doesn't point to the right place.
I see.
So basically, one possibility is that somehow your when you installed Anaconda, it should change your dot profile probably, and
Professor,
it should give this. You see, my installation changed my dot profile, and it gives basically it gives this F2Pi and Python in path. Okay, so what this actually does is it just changes path. Okay, in such a way that F2Pi from Anaconda is being used first before other F2Pis.
I see. I see.
Other F2Pis installed, and these are not the right ones. You should use the Anaconda one. So when you type which F2Pi, it should have Anaconda in the path.
Yes, it has Anaconda in the path, actually.
It has Anaconda in the path. Okay.
Yes.
Okay.
The only difference between my path and yours is like besides the name and it's the OPT. I don't know whether like it's under OPT.
I see.
This is Professor, if I could interrupt.
Yes, please.
This is actually an issue recently with the, you have a Mac that you're working on?
Yes.
Yeah, this is an issue with the GUI installer for Anaconda versus the command line installer. The command line installer actually installs everything correctly, but one of my undergraduates that I'm working with had the same exact issue, and we had to uninstall and reinstall with the command line installer.
I see.
So everything got linked properly.
Yeah.
Thank you. Thank you so much.
Thank you,
Nicholas. So I didn't know about that. At the time when I was installing, this seems not to be an issue. It wasn't an issue, but things change very quickly. Yeah. So okay, now it seems that unfortunately the homework, your last homework got harder. So you need to uninstall and install once more. Very sorry, but yeah.
Yeah, we can just try it. Yeah.
Okay, please try again.
One note is that the command line installer actually, to be honest with you, is a bit easier to use. You just execute the command line installer. It's a bash script, and it pretty much does everything for you. There's a couple things that you have to agree to, but then other than that, it does everything.
Sounds great. Thank you.
Yeah. Thank you. I didn't know. Okay, now hopefully F2Pi, on at least for most of us, if most of you works, then this command should execute without errors. Now this code is not yet OpenMP parallel. Since it's easy to add OpenMP directive, we are going to add here the following flag, --, F90 flags. This is like giving an extra option to Fortran compiler, and then inside this quotation marks, we're going to write the exact option F open MP, and now when we compile here, F90 compiler, for example, this fopenmp is indeed being used, which means that the code is probably OpenMP parallel. Now, how do we check that something really worked? Well, if I do ls minus ltr, I will see the file mandel some name.so has appeared. So the important point is that it's the name of the file is mandel, like I gave the name minus m mandel, so it has to have a name mandel dot. Now it turns out that in Python 3 it appends some name that I don't know exactly how it's being generated, but it's some generated name, Ceton38 Darwin, and then .so. In the previous version of Python 2, I think this intermediate thing wasn't there. But it seems that Python can ignore this part. So basically, you can think of it as having a normal module which has the name mandel. That's it. Okay. So now if I want to use this module mandel, I go into Python, and then normally you would just write import mandel and you can use it. Now, on my computer, surprise, surprise, doesn't quite work. Okay, and I had some issues this for a long time. I didn't figure out what's wrong. Well, it turns out that again in my version, in my installation, or in my Python 3 installation, it turns out that I need to import NumPy first, because this F2Py is actually part of NumPy. So if I do from NumPy import star or SkyPy, I usually do SkyPy, which already imports NumPy as well, then I can import mandel. Okay, I will need NumPy anyway, because I need NumPy arrays. So therefore, this is probably not a bug. It's actually a feature. So if I don't import NumPy first, I don't have access to arrays. And if I don't have access to arrays, then F2Py doesn't know how to properly work with such code. So now I have my mandel, and then I can write help mandel, and I can see that this module actually is what I expect it to be. So this is mandel, which is module is auto-generated with F2Py. Indeed, we generated it with F2Py. And inside we have just one function. And you see that here in this help, we already see that this code will return data to the dimensional array as result. Okay, data is going to be result. It's not going to be an input, but output. And then the rest of the variables are going to be, of course, needed as an input. But we also see that the SMAC steps that we changed with F2Py directive was an optional parameter. It's already given. It's already given as an optional parameter in Python, isn't it? What else? So yeah. Normally, I think we can also add some string. I guess I didn't add a string. Yeah, we could also add the string as the description of what the function does, but we didn't do it, so therefore description is kind of empty. But still, this minimal description is put there by default, so we have something. Okay, so for us now, this module exists, and this function inside the module mandelb exists, and we can use it and produce the mandelb plot. So I'm gonna use manp.f Python code, which, as you can see, is very, very short. Well, let me present it on this screen. It's the same code. Okay, so let me very quickly walk you through, but the code is really trivial. We first include import Skype, then which is the package that includes not only scientific Python but also NumPy. So we don't need to import NumPy separately, because Skype already imports NumPy. Then PyLab is Python lab for plotting. We need to of course import that because we're going to plot. And then we have this extra thing which is called import mandel, because this actually imports our F2Py module now. And then we're also import time because we're going to time things. Then, of course, we're going to set the range for plotting. Then we're going to look at the wall time and CPU time. And then the important statement here is this: data is equal to Mandel B, and this line. This is actually the statement that calls our Fortran function. So once more, the Fortran function is inside module Mandel, and the name of the function, so there's dot, and then there's the name of the function, which is Mandel B. Okay, and the input variables are X, which needs to be an array of 4 numbers. Indeed, it is. If it wasn't, there could be an error. And then it also needs to nx and ny, which is 1000 by 1000 in this case. Now, at the end of the day, we're also going to transpose this thing, because for plotting, we need, you remember the way the plotting works is that we don't go horizontally, but we start vertically, doesn't it? So that requires transposition of the data, just the way the plotting imshow works. Of course, this transpose doesn't need to be done here. It can be done instead here in this part where we display the data. It doesn't matter where we transpose, as long as things are transposed at the end of the day. So the step here, imshow, shows the data that's being obtained. And now there are some parameters that I gave here. I added interpolation of the data. So if it turns out that there are more pixels than data available, then there is some interpolation that Python uses, or PyLab actually uses. And then I guess I use the origin here, that it starts to plot from the bottom to the top rather than from the top to bottom. I mean, this Mandelbrot set is actually symmetric, isn't that? So basically that origin doesn't do much right now in terms of actual plot. But when you zoom in, for example, if you want to zoom in, then you will see that if you don't have this correct origin, that basically the range doesn't make sense because the data is actually flipped to what you expect. The top and bottom are flipped. And this extra arguments, basically aspect ratio is 1, means that we want the particular size of the plot, that it has x and y aspect ratio to be equal. And then extend just tells imshow what is the range in x and y, basically what is minimum x, maximum x, minimum y, maximum y. And then when this is done, we write show and we display the results. Okay, so if we execute this, manp.py, oops, manpf.py, then it shows the Mandelbrot set pretty quickly. Okay, now this one is of course not dynamic because we didn't code this dynamic thing. You see, if I zoom in, it doesn't change the plot, but you do see that it doesn't have a completely that the data here is kind of fuzzy, and the reason for this is because it uses interpolation. Okay, it's not step. We don't use the step-like plotting, but we use this interpolation, which is called bilinear interpolation. Therefore, the color changes gradually. But that's a minor detail. So from this plot, you don't see it actually, that it's using interpolation. Now, the important point is that the execution, the execution is very, very fast. You see, in my computer, the execution was 0.3 seconds in wall time. Of course, in clock time is more because I'm using OpenMP. Now I'm using very large number of cores as far as I know. So export OMP num threads. I don't know if I explained this, but export OMP num threads is basically, with this, I'm changing environmental variable OMP num threads, which specifies how many cores I'm using when executing some executable. So OMP num threads means I'm going to use only one core or one thread actually. And in this case, of course, clock time and wall time are the same, and I have 1.4 seconds on my computer. And if I increase this to 16, because I have 8 cores and each of them can support 2 threads, for example, then I get wall time to be down to 0.3 seconds. So that's extremely fast execution, isn't it? Extremely fast. That's the best we could get with Fortran or with C. Basically, it's as good as it can get. So the important conclusion from this exercise is that Python code is really simple. Fortran code, maybe you don't like it really, but on the other hand, is standard Fortran, okay? And with this little trick of executing F2Py, we were able to get basically the best possible performance. You cannot beat this code by writing it completely in Fortran or completely in C. So we get as much as possible from your computer. Okay, so this is F2Py. Any question? Does it work for everybody? No, let me ask you the other question. Who managed to get F2Py working?
I did that.
You did? More?
Yeah.
Anybody else? Yes? More? Huh. Yeah, well, if it doesn't work yet, I would suggest that you kind of play with your computer a little bit. If you don't manage to get it working, it's not a disaster because you will still be able to do many other things, but it would be nice if you spend some time and get this done, get this working. Okay, so next step is do the same thing with C++. Now, doing coding things in C++ is kind of easier in the sense that C++ is higher level language, but on the other hand, combining C++ with Python might be slightly more challenging because there is no C2Py or code like that, which comes with Python package. We had to install ourselves. I was asking you in the first homework to install something which is called PyBint 11. And this is not something that is standard. It's not something that is, how can I say, comes with NumPy, okay? But it's an add-on. It's a project that several volunteers have done it in the GNU type of environment. It's still very much alive in the sense that it's still being developed by your colleagues. I mean, mostly students actually. I think it's a great tool, but it's a little bit more complicated to use, of course, because C++ itself is a complicated language. So how does it work? Well, first thing is that you need to, the good thing is that this PyBint 11 does not use any libraries. And as I said last time, this is an advantage because combining libraries on different computers is always a headache because different computers have different chips and different environment, different operating system, and it's hard to compile these things or make them compatible. But the header files are basically the source files which are needed in PyBint 11. So we need only source files. Source files are very easy to transfer from computer to computer because they're always the same text files. So this PyBint 11 uses text files only or source files only. In this case, include statements. So we include several header files, so-called header files. And they are supposed to be found under PyBint 11, and then their name is either pybint11.h, which is like basic definition of things in this particular package. Then numpy.h is obviously, it describes or defines NumPy arrays, and STL is something that defines how to transform standard template library objects into Python objects. And then in addition, we have this include statement, include cstdint, which basically is one of the standard C++ include statements. This is not part of PyBint 11. Now, where are these files actually located on your system? Well, that depends a little bit on the installation. It's not the same on every compiler, on every platform, of course. If I go into my directory CPP, I have inside something which is called makefile, and I will look at the makefile directive. So here on the top, you have something which is called pybint. Okay, and this pybint variable is a variable that's being obtained by executing something, this particular statement. You see, there are this quotation marks, the quotation marks with one single quotation mark. This thing actually means when you define this variable, you execute this statement. Okay, that's what it means. When I define this variable, this statement inside the single quotation marks is gonna be executed. So if I install correctly PyBint 11, I can execute this on my computer, and it's supposed to give me the path where all this includes exist. Okay, and if I execute this a command, I see so-called include statements. This -i and path means minus capital I, path means this is a directory in which your include files might be located. Okay, and the compiler will go there and try to find them or search for them. Now there are only two, and I kind of know that the second one is the one that I use for PyBint 11. So of course it's inside Anaconda something, because I installed this PyBint 11 with Anaconda. And if I look at it, I see, okay, the only thing inside this path is PyBint 11. Okay, that seems to be compatible with how I write the include statement. So PyBint 11, and then inside should be something like stl.h, for example, which is some text file. You see some include file. We're not going to go into the details. Then there is a numpy.h, so it's another include file. And then we also used PyBint 11, PyBint11.h. You see, these are all three text files or include files that we're going to use. So once more, the compiler will get this path, okay, on my system. This is the path. And then relative to this path, the actual files are PyBint 11, PyBint11.h, PyBint 11 numpy.h, and PyBint 11 stl.h. Okay, and that's exactly what I used here to include these files, doesn't it? Include statements. Okay, so we know where these files are going to be taken, and these include files describe everything that has to do with conversion of C++ code into Python code. Okay, so from now on, we just read manual of PyBint 11 of how to use it. Okay, we need to know something about C++, and we can read the manual and figure out how the conversion works. Now, this code, C++ code, is not exactly normal C++ code. It's slightly different, and I will point out what is different. But this part, which is the function, okay, this one is, at least in this particular situation, in this particular case, is exactly the same as what you would have in C++. So it's a normal C++ function. However, this part down here, okay, the second part on the bottom, this is different. Okay, this is not a C++ code. Well, it's obvious because it starts with PyBint 11 module something. Okay, so this part on the bottom is actually the code that is defined inside this header file and connects, or basically connects C++ code or the function with Python. So the Python knows how to use this code or this shared library. Let me go through this code slowly. Let us go first through the normal Python, normal C++ code. So we are using at the top something that's called namespace pi is pymint 11 and using namespace std. So the first one just says that everything that is defined in, the second one says that everything that is defined in standard template library can be used inside this code. And the first one says that whenever I use something from pybint 11 namespace, I will need to prepend pi .. So for example, this pi .. is something that is defined inside this namespace pybint 11. Okay, a little bit details about C++, but the point is that that's one way to use these things. Okay, so now the input parameters here, the only non-trivial input parameter, of course, is this pi array. Because as I told you probably last time, is C++ does not have a standard multidimensional arrays. It has one-dimensional arrays, and the one-dimensional array is called vector. Okay, vector is one-dimensional array. Vector of integers means one-dimensional of integers. Can also be floating point numbers. So one-dimensional array easy, but multi-dimensional arrays standard C++ does not have. So therefore, it's not trivial or it's not straightforward to connect NumPy or multi-dimensional arrays with something in C++. Now, what pybint 11 provides is exactly such connection. So we can use a particular type that is defined inside pybint 11, which is called pi array t of double, and then the name is data. Again, we are using this symbol here. Do you remember what this symbol means? This symbol is called by reference, isn't that? Reference. So it means that we are gonna change this variable inside. We're not gonna copy it. We're gonna just use it with this name. We're gonna change it. Clearly, that's what we need in this case. We need to change this variable. And again, this particular statement here, this statement pi array t double and so on, this means that this is going to be this is a Python equivalent to Python array of double numbers, of floating point numbers. Okay, double in C++ is like floating point, float in Python. Okay, so this connects NumPy array. Then the rest are easy. I mean, nx and ny are integers in Python, and they're integers in C++. Well, there is a little detail here. Integer in Python is not exactly the same as integer in C++, but we are not going to we're not going to go into too much details, but basically it turns out that C++ integer has size of 4 bytes, and Python integer is much bigger. I think it's 8 bytes. So typically the two are not exactly compatible, but it turns out this pybint 11 will do proper conversion. So we are not gonna go, we don't need to take care of this, but sometimes you might have issues if you look at the size really, but this is automatically done. So that's another integer. Again, for us, it's gonna be integer in Python, translates integer in C++. Now, here we are using standard STL object, which is called vector of integer. This is something that exists in standard template library. It's something that C++ default exists in default. And it turns out that when using pybint 11, vector is translated into list. Okay, Python list. So vector of integers becomes Python list of integers. Okay, so again, this particular conversion is defined inside, I think, stl.h. Okay, so we know now the conversion and we know the variables, the input variables. Then the rest is relatively easy, except maybe one statement, which is somewhat non-trivial. So this very first statement here, we take the data, which is now this PyBint11 array or NumPy array, and of course we need to learn how to use it. Okay, because it's not something standard in C++. We need to learn how to use that thing, how to access the data, how to change it. And basically, we need to issue one command, which is called data. Data is, of course, the name of is the variable. And then we call a function on it, which is called mutable unchecked. 2 means it's two-dimensional, and then we say that this is a function. So basically, this is a so-called member function of the class. But the important point is that we said mutable unchecked. Now, this mutable unchecked means that variable will be changed. Okay, why? Because we're gonna change data array, isn't it? So it has to be mutable. And then unchecked means don't check the boundaries or make it don't check the boundaries if I'm writing beyond the boundary, because I want the code to be as fast as possible. Okay, uncheck means don't spend time on checking things. Of course, that's a bit dangerous, but on the other hand, this is how you get the most of the speed. Okay, so now I'm gonna set this data to something which is called dot. I'm gonna call it dot. Okay, and this type is gonna be auto type. Now, this auto is something that exists only in newer versions of C++, of C++ 11 and more and higher, which basically says that this might be a very, very complicated type that I don't want to type it out because it has a long, long name. I'm not going to deal with that. Of course, the name exists, but I don't want to write it. I'm going to write auto, and then I'm going to just use this variable as defined by people who develop PyBint11. Okay, so PyBint11 knows how what this particular object now is and how to use it. And well, I mean, it's used more or less in standard way we would expect. It's basically like a two-dimensional array in C, which uses the curly brackets. So basically, you can either read this two-dimensional array, or you can write the two-dimensional array, but using usual curly brackets, isn't it? Okay, so for practical purposes, all you need to remember is that we need to have a statement somewhere that converts somehow from this object a pi array into something that can be changed, is mutable, and we have to specify here this 2 here. The 2 specifies that it's two-dimensional array, because by default this pi array of double is of any dimension. So in this statement here, pi array of double, we did not specify dimension yet. So only here we specified the dimension is 2. And then we can use it as normally you would expect for two-dimensional arrays, isn't it? Of course, now we could do this any dimension. We could have 3, 4, 5 for any dimension. So in some sense, now we have in C++ multi-dimensional arrays which are compatible with Python, and that's perfect. That's all we need. And then the rest of the code is pretty much the same as before. We have this inside loop over number of iterations that we break out after we figure out that this point is not inside Mandelbrot set. Then we use complex number for z, complex number for z naught. We specify what is x and y in this two-dimensional grid. And by default, of course, we set this variable det to a maximum number of steps. And we iterate over the two-dimensional grid. Now you can notice here that I'm using also pragma statement, pragma OMP parallel 4, which makes this this three-dimensional loop OMP parallel. So we have parallelization over as many cores as specified in our environmental variable OMP num threads. Okay, so basically this is standard C++ code, though, with the only difference that we are using this special variable Python arrays, but otherwise it's very standard C++ code. But this part down here below, starting with PyBint 11 module, this part is particular to PyBint 11. Okay, so this part is particular to PyBint 11, and we need to read manual for PyBint 11 how to produce this code. It's actually relatively easy. So this PyBint 11 underscore module is basically something which is called macro. Okay, but for our purposes, it looks like a function. Okay, so we have like a function name with capital PyBint 11 module. Always needs to be specified in exactly this way, capital PyBint 11 module. Then the first variable, this variable here, is the name of the source file. Okay, source file. That's essential. So this first variable has to be the name of the source file. If it's not, there's going to be an error when you compile, turns out. Okay, so imanc is indeed my source file. Let me look at it here. imanc.cc is the name of my source file. I mean, of course, the ending of the source file is .cc, but I need to remove the extension .cc, and the name needs to be put here. Okay, imanc, essential. Now, this thing here, M, is basically a handle on my module. Okay, handle on module. With this, I have now an access to manipulate the module, because imanc will become a module, Python module. Okay, so what can I do with this module? Well, I can assign to this module documentation. For example, m.doc, I specify some string which assigns documentation to this particular module. Just like in Python module at the beginning and the top, you can give a string. Here you can give a documentation in similar way. Then next thing is I can add so-called def to this module. What does it mean, adding def to the module? Well, in Python, that would mean a function, doesn't it? So basically, I'm throwing now on this module, which is called M, a new function. Okay, so in other words, I'm linking Python function, which is going to be called mand_d. So this is the name. This mand_d here, the string, is named as it will appear inside Python. Okay, so Python function. So this is going to be named in Python. Python function, we have this name, mand_d. And then the question is, how is this related to any C++ code? And well, here is the connection. The second variable is an address. So this symbol here actually means taking an address of a function. So I know it's confusing in some sense because this variable was already used, this end variable was used before for call by reference, isn't it? We use it here on top as a call by reference. So call by reference, but when used in front of a variable, using the same symbol actually means taking a reference to that variable. Now, what does it mean taking a reference to that variable? That requires a little bit of knowledge of C++ or C. Anybody familiar with C will know this. Basically, it means that we are telling the computer where exactly in memory that particular thing is located. In other words, people who are familiar with pointers will understand this. Basically, we're taking a pointer to that function. Okay, so from a function which is a definition of something to do, we need to figure out a pointer or place in memory where this function is located. Okay, and that's what it's needed in order to create definition for Python. Okay, so I know it's a little bit complicated if you don't know C++ and C, but all you need to remember from here is that you need to use the symbol in front of the name of the function. Okay, and you create this def statement. Okay, so in some sense you can think of it as a black box. Okay, but I'm trying to give you some idea of what this actually does. So basically it needs a string here, which is any name that you want to give in Python, and then it needs so-called a reference to a function that exists. So this function here exists, and we take a reference on that function, and then we create Python equivalent. Okay, so now that this code exists, so I can look at it on my directory emanc.cc. Okay, exactly the same code, and I'm going to try to create a Python object out of it. Okay, I have C++ code. I want to create Python object out of it. Well, I don't know by heart. I need to use my makefile. Yeah, let me use only absolutely necessary things. So GCC, I'm going to use my GCC 10, which is GNU compiler, the real GNU compiler. -03 is optimization. It's not essential. -fopen mp, probably it's not essential either. Now this pybint level will become essential. So this will not work yet. I will need to add this thing, but let me remove it for now. So shared is actually essential. What does shared do? So shared option means that don't create an executable, but instead of executable, create so-called shared library. Actually, it turns out that shared library is almost the same as Python module. So a slightly modified shared library is actually the same as Python module. So therefore, if our compiler creates shared library with some little extensions, it looks basically Python will know how to use it. Okay, so therefore this -shared just means create shared library. Then -std is equal to C++11 specifies that some older compilers are not good enough to use with this F2Py. With this pybint 11. Turns out the pybint 11 needs standard, which is C++11 or higher. So the C++11 specifies that we are using more advanced options in C++. In particular, I pointed out this auto here. So this auto that, okay? So this statement is available only in C++11 or higher. So if I didn't specify -std C++11, then this statement will show up as an error, most likely. Probably still shows up as an error. I mean, I expect that in a few years from now, this particular option is going to be not necessary anymore, because eventually compilers will become compliant with C++11 standard. Now this fpic is an option that unfortunately on my computer is also essential. And it says that we need to create a code which is position independent. It's called position independent code. I mean, I don't want to go into details what exactly that means, but basically it means that somehow variables can be specified anywhere inside the shared object. Okay, and that's something that's essential when you create this Python code. And then basically we have to specify the name of the source code, eman.cc, and then name -o, and then name of the output, which is emanc.so. So This emanc.so is exactly the same name as I gave in this source code pybint11 module, when I specified before, has to be the same as the name of the source code and module. Okay, now this is not going to quite work yet. You see, it doesn't work because it says, I don't know where this pybint11.h is. Okay, so why is this a problem? Well, I'm using some include files, basically some files that the system doesn't find, my compiler doesn't find. Well, the reason for this is because I did not specify this statement here, Python 3. Okay, so I need to add this particular statement, which, as you remember before, it adds this -i directives. Basically, it finds where the include files are and takes care of the include files. This will still not work, turns out. You see, it compiles fine, turns out, the compilation is fine, but I have lots of errors when I link. Now, if you're using Linux, that will work, okay? You're done. With Linux, you're done. Unfortunately, under Mac, I had to read this the details about pybint11. Turns out we need to add another option, which is called undefined dynamic lookup. So, which somehow switches off the checks. If something is not defined inside this library, then some other library will be appended and it's going to be defined somewhere else. Okay, so that's going to be so-called dynamic lookup. And after I added all these options, now finally my code compiles, and I managed to get a file which is called emanc.so, and that's Python-like module. Okay, and I can use it just as normal Python module. So let me demonstrate this. So if I go inside Python and I do import emanc, you see this. I have the same issue. I need to do from SciPy import star. I was hoping I don't need to. Oops. No. Oops. I think I have an error somewhere. Make clean Y. Let me redo it. ePython import emanc. Yeah, now it works. Okay, so I clearly misspelled one of the options. Sorry, it happens sometimes. So if I don't misspell any of the options, then it seems I can import this module. And then I can do help on emanc, and it will specify, it will tell me that emanc is a pybint11 wrap for Mandelbrot. So it knows that that it was created from Mandelbrot with pybint11, and it has one function, mand, which is method of build PyCapsule instance, and it specifies what are the arguments. Okay, the return argument right now is none. So this is different than what we created with Fortran. Again, to make things faster, I did not want to return this time anything. So we are not returning anything. What we are doing is we are giving as a first argument NumPy array, and then this NumPy array is going to be filled. Okay, that's another alternative way, which is actually faster when executing. So the first argument is actually a NumPy array of floating point numbers. The next argument is integer, integer, integer. So there are 3 integers, and then finally the last argument is list of integers. Okay, list of integers. We say this was in C++ a vector of integers, which becomes Python list of integers. And then it also specifies where this module is. So now we can use this emanc just like any other Python module or Python file, and we can plot Mandelbrot set. Now this is done inside manp cpp.py. I mean, this is a little bit long source code, but it's but the basic things are very simple. I mean, what we really need is very, very simple. Let me demonstrate this on this screen on my iPad. So what do we use? We are gonna, all we need to do is we need to add a line which is called import eman-c, because we are importing this module. This is now a module, like Python module that we import. And then at the here somewhere, we're gonna use eman-c. What do we use it? I see. We're gonna use data is equal to month pybint11. So we are creating another function which is called month pybint11, and then it turns out that this function month pybint11, okay, is basically a function that that first initializes the data or creates the array data, then it calls the C++ code and then returns the data. Somehow I wanted to make this equal to the Fortran code, but it's not essential. So basically, we could just, if we wanted to, we could just inline just this statement and put it here. That would also work, of course. I kind of packed it into another function, but it's not essential. So in other words, all that you need to remember is that this is the way we call now this C++ code. So the first variable is data, because we need to allocate the data inside Python. So this is like an allocation of data and initialization of data inside Python. And then in C++, we just use this data. And then these are the other variables that are needed inside C++. Okay. And this is it. Then once we get the data, we can use our imshow to display and show it. Now the rest is just timing. Like always, we time both wall time and CPU time. And now, in addition to this pybint11, I'm also demonstrating at the same time how fast is our previous code done by Numba. You remember Numba? We discussed this last time. How the Numba speeds up the execution. We are going to now compare the two types of execution with speeding up by Numba and speeding up by pybint11. Okay, and I think in addition to this, I also had the usual Python, but maybe I didn't put it here because usual Python is so slow that we don't even want to bother. Okay, so I'm going to execute now. Hopefully, well, once I'm going to compile this once more just in case. And now I'm going to execute Python monp cppy, and yep, I got the plot pretty quickly. I'm killing this, and then I get a plot once more. It's identical, but it's done with a different way. So first one was done by pybint11, and second one was done by Numba. And as you can see from timings, pybint11 is almost 1 order of magnitude faster than Numba. Actually, my timing was showing me that it's 8 times faster than Numba, 8 times. Now, well, this is yeah. So this this large difference of 8 times comes mostly from using OpenMP. So if I do export open export OMP num threads is 1, then the speed up is not going to be that dramatic, but still it's substantial. So let's check. In this case, I have pybint11 is what, 70%, Numba is 70% slower. Okay, so it's still of the order factor of 2 faster PyBint11 than Numba. I mean, in many other cases, turns out that PyBint11 will be much faster. I mean, not just 50% or 60% faster, but it could be several times faster than Numba. But in this case, in this particular case, Numba turns out to be very efficient too. So somehow, Numba is of course way easier to use. But in generic case, I think PyBint11 will always give you basically almost theoretical performance. Okay, that's the difference. Okay, I have in the comment, in the chat, I have from Ankun that it turns out it was not a problem. So this problem of that we discussed before with F2Pi, I think, it wasn't a problem with Anaconda, but it's a problem with macOS and Xcode. So it seems that you don't need to reinstall. Is this correct? You don't need to reinstall the entire Anaconda once more, but it seems you just need to add something in the bashrc or prof.profile on your system to.
Yes, there's a forum. It says like with the upgrade of macOS, like they make the command line or they make the Xcode harder like to find the head files. So you just need to like lead the compiler to the head files.
Okay, so basically you don't need to do reinstallation again. That's the important point, isn't it? There's just some change in your bashrc, which is way easier than reinstalling everything. Okay, so, well, now we are basically done with F2Pi and PyBint11. You have a homework, speed up the implementation of Mandelbrot with this F2Pi or with PyBint11. It says or. Why or? Because I'm hoping that you might be able to get your system to work at least with one of the two compilers. Well, if you cannot do it with either of the two, then fine, then you don't do this homework. I mean, I understand it can happen that on your particular computer, you're not going to be able to set this up correctly because it's still a little bit of challenge on some computers. But hopefully most of you will be able to do at least one of the two, either Fortran or C++. And in this case, I would like you to execute this and make sure that it works. Now, again, if you're not familiar with Fortran on C++, I understand that you don't want to do this code yourself. You just take my code and you execute it. But if you're familiar with C++, you can recode. I mean, it's not a big deal. You can write it yourself. You can have my code as a cheat sheet and redo it yourself in a slightly different way. But what I would like is that you manage to execute this properly on a computer, okay? So that we are sure that your compilers are all properly set up. Any question?
I have two questions actually.
Yes.
So can you interpret the, can you go back to the makefile of the like?
Makefile here, this?
Yeah.
Yes.
Yeah, you have a argument like the -03 and you didn't interpret it. So can you tell us
Sure.
what
Yeah,
it's for?
Yeah, I wanted to explain this. -03 is just optimization. So if I don't specify it, then it's going to be some minimum optimization by default. -03 is usually the highest possible optimization. So basically optimize as much as you can. There are several this -O options. Capital O0 means no optimization. Capital O1 means some optimization. Capital O2 means much higher optimization, but don't overdo it, because sometimes when you use -03, the code might actually malfunction. I mean, it doesn't happen very often, so I usually try -03 almost every time, but it's not guaranteed to produce, to always work. In other words, sometimes the optimization of the compiler is so aggressive that your code might malfunction, might not produce results that you actually want. Okay, I mean, my experience is that this almost never happens, so I almost always use -03, but it can happen. And then there is one more optimization, which is called -O fast. In most computers, this exists as well, -O fast, which actually is -03 and then some other tuning parameters for your particular chip. It might be even better. But basically, it's just you tell compiler that you want the code to be as fast as possible, basically.
Okay, thank you for clarifying. And another one is, can go back to the makefile of the F2Py.
Yes.
Yeah, here is a dollar symbol and question mark, and
Yes.
also didn't interpret it. Yeah.
Yes. I wanted to talk about this. Basically, this is going to be the subject of next chapter. This is supposed to be basically. It turns out that this is so-called special variable. Okay, there are several special variables in makefiles, and this one particular one means the first thing on the right-hand side of this rule. So in this case, would be equivalent to saying that this is mandel.f90. Okay, so
okay.
basically, this is I should use mandel.f90 for let's say for this particular class, because I didn't yet introduce the special variables. But it turns out that special variable $? is the first object on the right-hand side of the rule.
Mm-hmm.
Yeah. So this should work to make clean make. Yeah. It works equally well. Yeah. Next time we're going to discuss exactly this. So we're going to discuss makefile, and then there are those. Yeah. So where are these special variables? So here we're going to discuss special variables. It turns out that this is $at, $less, $*, things like that. $question mark, I guess I didn't even specify. There are several, yes, that might be used in makefile. Okay, any other question?
Okay.
Anything else? No urgent question. Okay. So if you don't have anything, then I guess we see each other on Wednesday. And on Wednesday we're going to discuss a little bit about compiling, very quick discussion, and then a little bit about makefiles. Exactly these questions that Shang had. We're going to specify a little bit so that I can walk you through some basics of makefiles. And this is going to be followed by some discussion about parallelization and a little bit more introduction into OpenMP, so that we have a little bit more clear idea of what OpenMP actually does. Something beyond the simple pragma statement that we already done before. Okay, so I hope to see you on Wednesday, 5 p.m.
Yeah, see you.
And have a nice evening with a lot of snow. Sliding, huh? It was sliding.
Thanks, Professor. Have a good night.
Good night.